Welcome to a journey through one of the most pivotal experiments in modern physics, the Davisson-Germer experiment. In the early 20th century, scientists were grappling with a fundamental question: are electrons particles, waves, or perhaps both? This experiment, conducted by Clinton Davisson and Lester Germer in the 1920s, would forever change our understanding of the quantum world. Before we dive into the details, let's set the scene by exploring the scientific climate of the time and why this experiment was so groundbreaking. The dawn of the 20th century, classical physics was being challenged by strange new discoveries. Light, once thought to be a wave, also showed particle-like properties. Could the same be true for matter like electrons? This was the question that inspired Davisson and Germer. Their experiment would test whether electrons, which were always considered particles, could also behave like waves under certain conditions. This idea was radical and would require careful experimentation to prove. Clinton Davisson and Lester Germer were physicists working at Bell Labs in New York. Their collaboration began as a routine investigation into the surface of nickel crystals. Little did they know, their work would lead to a discovery that would shake the foundations of physics. Both scientists were meticulous and curious, traits that would serve them well as they embarked on their groundbreaking experiment. Heart of the Davisson-Germer experiment was a vacuum chamber containing a nickel crystal. Electrons were fired at the crystal, and a detector measured how they scattered. The setup was designed to observe how electrons interacted with the orderly rows of atoms in the nickel. By carefully controlling the angle and energy of the electrons, Davisson and Germer could study the patterns that emerged from their collisions with the crystal. Initially, electrons were considered tiny particles, much like miniature bullets. When fired at the nickel crystal, it was expected that they would simply bounce off in predictable ways, similar to how billiard balls scatter after a collision. However, Davisson and Germer were about to discover something far more intriguing than simple particle behavior. As the experiment progressed, Davisson and Germer noticed something strange. The electrons did not scatter randomly as classical physics would predict. Instead, they formed distinct patterns, bright spots at certain angles on the detector. This was completely unexpected and hinted at a deeper, wave-like nature of electrons. The patterns observed by Davisson and Germer closely resembled those produced by waves passing through a grating, a phenomenon known as diffraction. This was a major clue. If electrons were behaving like waves, they should produce interference patterns just like light waves do when they pass through slits or gratings. Nickel crystal in the experiment acted like a three-dimensional grating for the electrons. Its regular atomic structure allowed the electrons to diffract, just as light diffracts through a finely spaced grating. This setup was crucial for revealing the wave-like properties of electrons, as the crystal's atomic arrangement provided the necessary conditions for interference patterns to form. Fraction occurs when waves encounter an obstacle or opening and bend around it, creating patterns of constructive and destructive interference. In the Davisson-Germer experiment, the electrons acted as waves, and the nickel crystal's atoms served as obstacles. The resulting diffraction pattern was strong evidence that electrons could behave as waves under the right conditions. Results of the experiment provided direct support for the hypothesis proposed by French physicist Louis de Broglie. He suggested that all matter, including electrons, could exhibit both particle and wave properties. The Davisson-Germer experiment was the first to confirm this idea with tangible evidence, marking a major milestone in quantum theory. Wave-particle duality is the concept that particles such as electrons can exhibit both wave-like and particle-like properties, depending on how they are observed. The Davisson-Germer experiment was a turning point, providing concrete evidence that electrons, which were always thought of as particles, could also behave as waves. The patterns observed in the experiment could be explained using Bragg's law, which describes how waves are diffracted by a crystal lattice. By applying this law, Davisson and Germer could predict the angles at which the electrons would form bright spots, further confirming the wave nature of electrons. Conducting the Davisson-Germer experiment was no easy task. Maintaining a clean, well-ordered nickel crystal and controlling the electron beam required precision and patience. The equipment had to be carefully calibrated, and even small changes in temperature or pressure could affect the results. Despite these challenges, Davisson and Germer persevered, driven by their curiosity and commitment to scientific discovery. Interestingly, the most significant results of the experiment were discovered by accident. After a vacuum tube broke and was replaced, the nickel crystal was oxidized and then cleaned by heating, which created a nearly perfect crystal surface. This unexpected event allowed the electrons to diffract more clearly, leading to the breakthrough observation. Results of the Davisson-Germer experiment were a triumph for quantum theory. They provided the first direct evidence that electrons could behave as waves, confirming predictions made by de Broglie and others. This experiment helped to solidify the foundation of quantum mechanics and change the way scientists viewed the nature of matter. Implications of the Davisson-Germer experiment were profound. It not only confirmed the wave nature of electrons, but also paved the way for the development of electron microscopy and other technologies that rely on the wave properties of particles. The experiment demonstrated that the quantum world operates by different rules than the classical world we experience every day. One of the most important applications of the wave nature of electrons is electron microscopy. By using electrons instead of light, scientists can achieve much higher resolution images of tiny structures such as cells and molecules. This technology has revolutionized fields from biology to materials science. Davisson-Germer experiment was a catalyst for the rapid development of quantum mechanics. Scientists around the world began to explore the strange and fascinating behaviors of particles at the quantum level. The experiment inspired new theories and experiments, deepening our understanding of the universe. For their groundbreaking work, Clinton Davisson was awarded the Nobel Prize in Physics in 1937, sharing the honor with George Paget Thomson, who independently demonstrated electron diffraction. This recognition highlighted the importance of their discovery and its impact on the scientific community. At the same time as Davisson and Germer, British physicist George Paget Thomson was conducting similar experiments in England. He also observed electron diffraction, providing independent confirmation of the wave nature of electrons. The simultaneous discoveries by these scientists underscored the universality of quantum phenomena. Today, the Davisson-Germer experiment is a staple in physics education. It is often featured in textbooks and lectures as a classic example of quantum mechanics in action. The experiment's clear demonstration of wave-particle duality makes it an essential part of any physics curriculum. Building on the legacy of Davisson and Germer, modern experiments continue to probe the quantum world. Scientists now study wave-particle duality with larger particles, such as molecules, pushing the boundaries of our understanding. The principles discovered in the 1920s remain at the heart of cutting-edge research today. The insights gained from the Davisson-Germer experiment have fueled the development of quantum technologies. Quantum computers, sensors, and communication systems all rely on the strange behaviors of particles at the quantum level. The experiment's legacy lives on in the technologies shaping our future. The Davisson-Germer experiment also raised profound philosophical questions. If electrons can be both waves and particles, what does this say about the nature of reality? The experiment challenged scientists and philosophers alike to rethink their assumptions about the physical world. Before the experiment, the world was seen through the lens of classical physics, where objects had definite positions and velocities. The discovery that electrons could behave as waves forced a shift in perspective, opening the door to the probabilistic world of quantum mechanics. Davisson-Germer experiment is closely related to the famous double-slit experiment, which also demonstrates wave-particle duality. In both cases, particles like electrons create interference patterns when not observed, but act like particles when measured. These experiments together form the foundation of quantum theory. One of the most intriguing aspects of quantum mechanics is the observer effect, the idea that the act of measurement can influence the outcome of an experiment. The Davisson-Germer experiment, like others in quantum physics, highlights the mysterious relationship between observation and reality. The success of the Davisson-Germer experiment depended on careful experimental design and precision. Every aspect, from the purity of the nickel crystal to the alignment of the electron beam, had to be meticulously controlled. This attention to detail set a new standard for experimental physics. Electron diffraction is now a routine tool in laboratories around the world. Scientists use it to study the structure of materials at the atomic level, revealing details that are invisible to traditional microscopes. The technique owes its existence to the pioneering work of Davisson and Germer. The principles demonstrated by the Davisson-Germer experiment extend beyond electrons. Other particles, such as neutrons and even atoms, have been shown to exhibit wave-like behavior under the right conditions. This universality is one of the most remarkable aspects of quantum mechanics. The Davisson-Germer experiment marked the beginning of a new era in physics. It helped to usher in the age of quantum mechanics, a field that continues to expand our understanding of the universe. The experiment's legacy is felt in every corner of modern science. Because of its clarity and significance, the Davisson-Germer experiment is often used as a textbook example of quantum phenomena. It provides a clear visual demonstration of concepts that are otherwise abstract and difficult to grasp, making it an invaluable teaching tool. The story of Davisson and Germer continues to inspire new generations of scientists. Their curiosity, perseverance, and willingness to question established ideas serve as a model for anyone interested in exploring the mysteries of the universe. Quantum mechanics is famous for its counterintuitive and sometimes bizarre predictions. The Davisson-Germer experiment was one of the first to reveal just how strange the quantum world can be, challenging our everyday intuitions about how nature works. Behind every great scientific discovery are the people who make it happen. Davisson and Germer's dedication, creativity, and openness to unexpected results were key to their success. Their story reminds us that science is a human endeavor, driven by curiosity and the desire to understand. Since the 1920s, experimental techniques have evolved dramatically. Today, scientists use advanced equipment and computer simulations to study quantum phenomena in even greater detail. The spirit of innovation that drove Davisson and Germer continues to shape the future of physics. The Davisson-Germer experiment began as a simple investigation into the properties of nickel crystals. Through curiosity and careful observation, it led to a discovery that changed the course of science. This story highlights the importance of asking questions and following where the evidence leads. Nearly a century later, the impact of the Davisson-Germer experiment is still felt. Its lessons continue to inform research, technology, and education. The experiment stands as a testament to the power of scientific inquiry and the enduring quest to understand the universe. The success of the Davisson-Germer experiment underscores the importance of evidence in science. By carefully collecting and analyzing data, Davisson and Germer were able to challenge established ideas and reveal new truths about the natural world. The quantum revolution sparked by experiments like Davisson-Germer's continues to unfold. New discoveries and technologies emerge every year, building on the foundation they helped to establish. The experiment remains a symbol of the transformative power of scientific discovery. To summarize, the Davisson-Germer experiment demonstrated that electrons can behave as waves, confirming the predictions of quantum theory. This discovery changed our understanding of matter and paved the way for countless advances in science and technology. As we look to the future, the principles uncovered by the Davisson-Germer experiment will continue to guide scientific exploration. New questions and challenges await, but the spirit of curiosity and discovery that drove Davisson and Germer remains as vital as ever. The story of the Davisson-Germer experiment is a reminder that great discoveries often come from unexpected places. By remaining open to new ideas and following the evidence, anyone can contribute to our understanding of the universe. The experiment continues to inspire scientists and dreamers alike. Let us celebrate the spirit of scientific inquiry embodied by Davisson and Germer. Their experiment stands as a shining example of how curiosity, perseverance, and careful observation can lead to discoveries that change the world. The legacy of their work endures in every scientific breakthrough that follows. Thank you for joining us on this exploration of the Davisson-Germer experiment. From its humble beginnings to its lasting impact on science and technology, this experiment remains a cornerstone of quantum mechanics. Its lessons continue to shape our understanding of the universe and inspire future generations of scientists.